So this is my quiz correction. What answers the standard? I can calculate fields or lines in planes and their effects of uncharged dipoles. And the question that I chose to answer was 2100, which is one of the recommended ones, which reads, two very large parallel sheets are 5 centimeters apart. Sheet A carries a uniform surface charge density of negative 9.50 microcoulombs per meter squared, and sheet B, which is to the right of A, carries a uniform charge of negative 11.6 microcoulombs per meter squared. Assume the sheets are large enough to be treated as infinite. Find the magnitude and direction of the net electric field these sheets produced at point A, which is 4 centimeters to the right of sheet A, B, 4 centimeters to the left of sheet A, and C, 4 centimeters to the right of sheet B. So what I started was with a force diagram showing that for point A that the forces would be working against each other because it's between the two sheets. And here's where I kind of made a conclusion, because I couldn't find an equation that had radius for an infinite field, or an electric field. And then I remembered in class you talked about how it didn't really matter where you picked, and then we went over that again as one of the commonly asked questions. So I'm thinking that the reason them giving us the 4 centimeters apart is just to give us a location as far as like if it's in between the two sheets, to the right of the sheets or the left of the sheets, and it doesn't actually have any impact on the net electric field that's produced by the two infinite sheets, because I couldn't find one since I think that makes sense, but if not, I can redo this. But so I said the electric field is equal to the lowercase sigma over 2 epsilon naught, which is just the equation that we had. So I said the sum of the electric fields for the first point was sigma B, which was given to us over 2 epsilon naught, minus sigma A, which was given to us over 2 epsilon naught. And they'd be subtracted from each other since they were both facing opposite directions. Or since they were both negative charges, the point in the middle would be experiencing them, one pushing it to the left and one pushing it to the right, like my force diagram showed. So I had 11.6 microcoulombs per meter squared minus 9.5 microcoulombs per meter squared over 2 times I looked up the epsilon constant, which was 8.85 times 10 to the negative 12 coulombs per Newton meter squared. And then I multiplied the two values on top by 10 to the negative 6 since they're microcoulombs per meter squared, and I got the total 118,644.06 newtons per coulomb. And this, I said, was directed to the left because the charge on the right plate, or plate B, was larger than plate A, directing the charge to the left or away from it, since it was like net larger than that. But for the next one, the point that they described to us was, let me look back in the book, 4 centimeters to the left of sheet A. So in this case, both the charges were working, or were applying their force to the point in the same direction, which was to the left as well. And so the only difference in this one is rather than subtracting the sigmas, I added them together, which I did the same thing with 10 to the negative 6, and that yielded 1,192,090.395 newtons per coulomb, and that, like I said, is directed to the left since both the sheets' electric fields are working towards the left. And then for C, its point was described as 4 centimeters to the right of sheet B. So if I was right and the radius doesn't matter, that the directions would just flip and it would be the same math. So I would just do the same math as B, but rather than being directed towards the left, it would be directed towards the right. That's because the radius doesn't matter for an infinite sheet.